Hi, everyone. Thanks for tuning in to the Printed Circuit Podcast, where we'll discuss trends, challenges, and opportunities across the printed circuit engineering industry. I'm your host, Steph Chavez. In this episode, we'll focus on multi-board design. And here to join me in this discussion is Chris Young, owner and lead engineer at Young Engineering Services. Thanks for being here, Chris. Thanks for being here again. At least let me say that.
Yeah, my pleasure.
For those that didn't check out our episode on concurrent design, can you give our audience a brief introduction of yourself, Chris?
So I'm an electrical engineer, got over 2 decades experience designing circuit boards, systems, test systems, writing software. Initially, I started off in the semiconductor industry, went to semiconductor test, avionics, and then I've been doing my own consulting business for over a decade now, where I focus on providing development platforms for customers so that they can actually have designers be more successful in their designs is primarily what I've been focused on lately.
You and I go way back. We've collaborated on many designs, both easy to very extremely challenging, especially when you talk about form factor or multi-board design and from the different speeds and the different spectrums where you talk about mixed signal, analog, digital, RF, high power. I really want to get into this with you. So when we talk about multi-board design, can you tell me what doesn't work today when it comes to multi-board design from your perspective?
So I think what doesn't work today is the designs are done separate from each other. So if there's like 3 boards that make up a simple system, you got 3 boards. One might be the brains of the operation, which is like a microprocessor I/O board, and one's a power supply board, and the other one might be an interconnect card that connects the boards together and then to the outside world. Typically, those design teams or designers for those individual segments will be working separately from each other. And their only means of communication is typically maybe some conversations and some spreadsheets, which makes the whole overall system rather opaque to the individual designer. So there's always a lot of questions that comes to mind of like, well, okay, so I know I need a digital signal out here. What type of signal do they really need? Is it a CMOS signal in terms of, do I need like a TTL signal, like 5 volts, or do I need a low volt CMOS, 3.3 volts, 2.5 volts? So, what you'll end up with is things like incompatible signal levels. And what I consider critical issues is that the pinouts don't match. So it makes it difficult if you don't have some type of overlying model to help represent the system. Today's marketplace, I typically see maybe some system diagrams and then some spreadsheets to manage the interconnectivity, and that's about it. And everybody else the individual designers are left to their own to try to hopefully make it work.
I've seen my fair share of engineering teams where we were attacking signals as they traverse through the system, and that manual approach, it's long, it's tedious, and time consuming. And I would tell you, there's so much potential for errors. I mean, we're human and humans, make mistakes. What popped in my head real quick is the last time I was on a team where we had 4 EEs attacking a multi-board system. And believe it or not, one of the pinout from one board to another, one was power and one was ground, and nobody caught it. And we didn't catch that. And individually, the boards were great. When you put them together, it was a problem. And you talk about catastrophic problem because instant short and fire, or should I say, circuits blow like fuses, traces blow like fuses. So, we know what the problem is or what it can be, but what is the solution or the best practice for PCB designers that they should implement?
Well, I think the integration of the tool chains across from basically systems, software, let's say the PCB designers and mechanical engineering, like creating like a digital thread, basically, that links all of these components together, some type of mechanism that can pull that together and then keep track of things like the changes. Because that pinout mismatch that you talked about, well, that might be they may have had to change the pins on one of the boards. Initially, it could have all matched up and synced up, and then someone said, oh, you know what, we've got this layout issue, and I can't quite get what I need to do without swapping these 2 pins. That information doesn't get transferred back. So if you have some type of system level model of what is happening through some type of mechanism, I know that Siemens EDA has a solution that is headed in the right direction, I think. But, the reality is that a picture is worth 1,000 words. We've heard that before. We've heard it. Well, a model is worth 1,000 pictures.
That's great. I love that analogy.
So what it does is the system is rather opaque if you're designing in silos. Some type of digital link between all of this, thread, chain, whatever you want to call it. I think there's a good definition for a digital thread out there that shows the tool connectivity from design concept to production. It'll help make the design transparent. So if you make a change, the other people working on the other boards, the other designers will go, oh, that changed. We need to do something about that. So building a robust tool chain that enables that digital thread to traverse from the system down to the individual components that are being designed, I think is really a good solution for this type of problem.
The thing that gets me is that I'm surprised, especially when you think about the system as a whole within the project and then the customer timeline and the budgets. I'm surprised how many engineering teams don't have a model-based systems process in place to be able to model the entire system, especially when you talk about very complex designs and you pretty much got like one shot to get it right. And, we're doing a lot of manual steps, and that may have worked in years past, but today we can't have that. It's not going to cut it. And you talk about the speeds when you're traversing from one board to another. I mean, what is the quality of the signal as it goes through the connector, as it loses impedance or loses its signal integrity? I mean, or you have EMI issues. There's so many things to deal with. And without modeling that system, it's a challenge. And I always feel that you're kind of like in a dark room trying to throw a dart and hit a target with your eyes closed when you're not, using a model-based system approach for engineering. So can you walk me through some examples of how you would see that this would work?
I can walk you through some of the stuff that I've encountered in my career. One of my first large-scale designs that I participated in, I was responsible for a relatively complex dual processor I/O card. There were 3 FPGAs on the board. There were 2 high-end embedded processors. There's Ethernet, and you name it. There's just a myriad of different interfaces on this board. So the difficulty I had there with that board was actually, is this going to work with the other boards? And we thought it did. And then we came across a very strange behavior. We put the system together. We think it's working. Then someone comes to us and go, hey, when we turn the box on, it transmits. Before it even boots up, it's transmitting an RF signal. Do you guys even know what's going on there? And what came down with the pipe was that there was incompatibilities at the signal level between the 2 boards on power up. And what the real issue was is that the sequence of power up was the power supply would power up, the RF board, the transmitter, was tightly coupled to the power supply. So the power supply and transmitter were powered earlier and way ahead of the processor. And I say way ahead, I'm talking milliseconds, which can be very significant. And in this case, it turned out to be critical. So the processor, when it was unpowered and started to power up, there was an ESD diodes inside an FPGA that were holding down the input of a signal buffer. And that signal from that buffer was actually trolling the gating to the transmitter to turn it on. And it would transmit. And that was a very hard discovery because we discovered that right before we were going to go into certification testing. That was a rough deal. We were very fortunate in the sense that the power supply engineer was able to mitigate it on his board. So I caused a respin on another board because the processor I/O card was mine. Not having that would have been great. Now, an example of where using some type of, I would say, beginnings of having a systems level model, my first real experience with this was actually using the multi-board SEM and hyperlinks. We had another design. We're all a little bit wiser from some of the mistakes that we made from the first large design. So you go into this and you're like, okay, so we've got this LVDS signal that's traversing its way from a processor card through an interconnect card to a receiver card, an RF receiver card. maybe we need to figure this out and model this before something happens. And sure enough, we took the design as they were. This was the prototypes. We exported out the board sims, the board files, for hyperlinks. We used the multi-board sim functionality within the hyperlinks tool. And we're like, oh, wow, we have problems on both the interconnect card and the receiver card. And this would have never worked. That's a very hard problem to deal with once the board's built. It's a sensitive signal if done improperly. So we were able to flush that out, and it worked. And it was like, oh, well, thank goodness. And the insight was being burnt hard from that first design. And second design, you get in there, and you're like, man, we got to do something. And then the natural, like a very natural solution was to be, we need to have a model of what this entire chain of components is doing. That was my practical introduction to like a systems type modeling. Not nearly as complex as like having a whole systems modeling software, but indeed it was immediately and directly useful, and it prevented us from getting ourselves hurt.
The biggest thing that I see, or the keys here, are communication, communication, communication. You cannot communicate enough within your team or all the stakeholders. That even includes your external stakeholders. I also think working in silos, we can't have that anymore. I mean, that's got to go. Now, those walls that separated have to come down. And as you mentioned earlier, if a change is made in a system, today's tools and functionality and the capability within, like a model-based engineering is to be able to design the entire system. And if one domain makes a change or one discipline makes a change, like let's say, for example, a double E makes a change with the designer on the board and we move something, that move is instantaneously suggested and posted to all the other disciplines, and they either accept or reject that change. And it's constant communication on the fly. And I think that is the key. And being able to have that instantaneous feedback when you're designing, so that way all disciplines are involved and have visibility to the intelligent decisions being made is key. And I can't see the manual approach that we've been doing for the last few decades to continue going forward as our designs are getting more and more complex, especially when we talk about the high speeds, low power, everything is getting smaller and smaller, or it's high power and we're still trying to get as dense can be. And you're talking about HDI, microvias, micro traces, sub-micro traces. It's just crazy. It just amazes me. So, Chris, you've outlined some good examples there. So, what do you see as the roadblocks to implementing this kind of best practice or these best practices that you and I would suggest, or what we've learned over the years?
I see two major roadblocks. One we covered back when we talked about concurrent design is that people have a solution that's already working. And why would I change that solution that's already working? And it's a valid argument on its face, and definitely sometimes even in context, it's a valid argument. However, it's still, the way you combat that is you take what's causing that type of resistance. And then the second part of this challenge here is something, it's called learned helplessness. And it's a terminology used in psychology, and what it basically says is that it's a state that occurs when a person has experienced a stressful situation repeatedly or intensely. So what it means is that sometimes this resistance to change is a learned behavior because of hard times that they've had during maybe past projects, where they go through, and what can be a very hard situation for any type of project team is to go through multiple respins on a project. The first spin you got to go through, and you go to your management, you go to upper management and go, hey, we're not going to meet schedule because the system doesn't work. We're also not going to meet our budget for the project because we got to buy it all again. We got to do everything again, or do large portions of it again. And then you come to them the second time and you say, hey, I know we've talked about this before, but we're not going to meet the new date either because the system still doesn't work. And we're still going to go over budget yet again because we need to make it work, and this is what it's going to take. Those type of experiences for a large-scale project can be very stressful and traumatizing, quite frankly, Because the people that are involved, you always think to yourself, did I just lose my job? That type of stress can lead you to some type of mentality where you're saying, well, I tried something new once and it failed so spectacularly that I'm not going to do that again. I'm just going to stick with what works and what I know. You see this with decoupling capacitors. They'll be like, I'm going to have a zero 0.1 microfarad, a 0.01 microfarad, and a 0.001 microfarad on every single power rail, no matter what, because I'm not taking any chances. So the way to deal with this learned helplessness, it's antonym. It's learned optimism. It is literally about taking the experiences that you've had, thinking about what you've learned and what you know better now so that you can proceed. And the way that you use this is, well, if you're talking to a management, in terms of the lower level management, this would be the project management and the disciplinary management, which is the, software, hardware, mechanical, you name it, right? Systems engineer, a systems manager. And you start asking them questions from a positive viewpoint, though. You'll be like, okay, so here's your process. Why are you so resilient to change on this process? What got you here? Can you explain to me what happened? You talk to them about their project and you go, oh, wow, that really, you had to do two systems level respins on your project. That had to have been a hard time. However, I bet you learned a lot from it. And you start looking, then you break down the details of their process that they have. And this is most likely a manual process, because I've encountered very few companies that have a system level model of their stuff. It's usually, again, a system diagram and spreadsheets for interconnectivity. And you draw parallels to your system modeling solution that you have. And you go, oh, okay. So what you want to do is show similarity of your system level modeling solution to their current process. That builds confidence in them. And then you talk about their lessons learned in a positive manner. It's not, people a lot of times learn, don't touch, that's hot. Don't touch the stove, it's hot. You burn yourself once and you're like, wow, I'm not doing that again. But you take that approach of like, okay, so we know not to touch the stove, but you still have to clean the stove, right? Well, what if you just make sure the stove's turned off before you touch it, and check it for heat, put your hand close to it, but don't touch it. And that's the type of approach that you take with the systems level approach. You could be like, okay, so you've got your system block diagram and you have your Excel document for interconnectivity. Well, what if I said that this Visio diagram that you have, most places I work with use Visio, what if you were able to import that into our tool? What if we had an equivalent thing? You can still draw your Visio diagram, but you can put it in the tool, the solution that we have. Again, I'm speaking from a standpoint, I don't know if Siemens has that specific capability, but oh, well, that's great. That's the thing. You're like, hey, you can take this thing that you're used to doing and you can do it here too. In fact, you can do it here and pull it directly in. And now you can start seeing this. Then, so what I see here in your spreadsheet is that you can horizontally link signals together between different interconnects, different connectors. I see that as a common practice. They'll have columns will be connectors, rows will be the pins, and you can look across it sideways. Then you show them in the tool. Hey, look at this. You can see the trace left to right through the system, through the boards, that this connectivity is there. So this whole process of lining things up and tracing across horizontally, we have a mechanism for that too. You make that solution similar. I shouldn't say make. Well, in some cases you'd want to make. I'm a proponent. There's always opportunity for improvement. So that you can explain the tool, and you start going into this detail. You can even see that yourself on your tool. You can say, "Oh, hey, what if we made this improvement that was close to your process? Because this kind of makes sense to us in a logical manner. This, part of your process makes sense. We don't have it captured here, but what if we look at pulling it in? Can we have more conversations with you about that? Can you help us do that? That will bring them in, and it helps them deal with that type of mechanism, that learned helplessness, It turns it into a learned optimism. It just kind of breaks them free of that kind of quagmire that they've found themselves in.
When I think about those two terms of learned helplessness or learned optimism, I think about my experiences in large enterprises, especially in the mill era, where you have internal company culture resistant to that change, and it's because you've had people that have been with a company for like 30 or 40 years. They stay in their comfort zone or in their pocket of success, and they don't deviate. They stay within what has worked for them, like you described, and they continue to do that old methodology on now more and more complex design or more systems where you have multiple boards. And the only way to evolve and to be able to afford to do these very tough designs on tough budgets and tough schedules is to have multi-board, a system level model based approach in designing the system. And internal company culture is one of the biggest roadblocks, and it's a hidden roadblock that people don't realize inherently that they are imposing their own self-restriction because they're not open to change, whether it's changing their process or evolving to a tool that's much more feature rich and feature capable of handling these advanced design processes to be more efficient. And some people may perceive it as, well, it's too expensive to change. Well, I will counter that and say, what is the cost of not changing? What is it going to cost you in the long run? And it surprises me how much money is being left on the table because company cultures is resistant to the evolution of change, whether it's process or tools or their methodology approach in multi-board design. So that's immediately what pops into my head, the entire time you were speaking. So let me ask you this. How do you think someone can overcome or companies can overcome these roadblocks within the organization or within the culture themselves?
One approach is to be persistent and consistent in what you're saying within the organization. That means something to people. If you're gonna say something and just bring it up once and then someone bats it away and you're not gonna come back to the table and say, hey, what's going on here? I still want to do this. You could be talking to your manager, you'd be like, I think this is a good idea. And they say, no, we don't have the money for it. Or, no, I disagree with you. If you leave it at that, well, then you're done, right? It requires someone that is consistent and persistent about what they're trying to do. This is why a lot of CEOs, founders of companies, are so successful. They're consistently driving and persistently driving towards a goal. It's going to happen. That's for an internal employee. I think that when you're coming from an approach of if you're an inside sales guy or something like that, or, you're trying to make a sale, when they talk about cost, right? It's a hard sell to say this tool is going to make your design so much more efficient that you'll be able to get it done faster. Now, where you can win out is things like this. And I'll talk specifically to maybe some avionics experiences, which is, in avionics, when you go to certify design for whatever, if you're going for a type certification or you're looking for a TSO, a technical standard order certification, you have to provide the FAA with plans, preliminary hardware plans, preliminary software plans. And then at the end, you have to give them your accomplishments. How did it go and what did you do? How'd you deviate from the plans, right? And then they have other processes in between, DO 178, DO 254, so that you have testing artifacts from their MOPS testing, minimum operating procedures. Those cost money. When you get down to some certain elements that are directly related to the board design, I can think of two things, which is, if you're going to spend the time to put the systems definition in the model, you would want a mechanism that the model or the software, the application can output an artifact that is representative of the model in documentation form. So that you can say, you don't have to spend your time writing a bunch of documents to define the system. You define it in here and it outputs the document that you need to provide the regulatory authority in order to achieve certification. Another big thing that pops out at me which is an excruciatingly detailed task, which is failure modes effects analysis. I've worked on systems where it's multi-board design. Inside that design, there's like 5, 6, 7,000 components, tens of thousands of connections. And you have to go through in a very detailed manner and identify the failure modes and how it affects the system behavior. Now, that's the type of approach that can take man years, and it literally has in the what I've encountered in my career. And if there was a way to reduce the effort, that would be great. In terms of like, if you've already logically organized your system design in the model, and then you have visibility down to the component, to the specific design, the specific boards, then you can actually functionally group the circuits. You can have functions that automatically group those circuits together and lay it out. As the designers are putting notes in there, they can actually fill in information while they're designing to show what the failure modes are, instead of trying to think about it as an afterthought. Because I can tell you that when the designers are doing the design, I'm not talking about the PCB design, I'm talking about the electrical engineers, which might be the same thing. I mean, I know that some companies are having electrical engineers do the board layout and do the PCB design as well. But when you're designing, you're coming up with these circuits, these functional circuits to be able to accomplish your goals. I mean, you're thinking about the corner cases. It's not going to work if it doesn't meet the corner cases. And you're thinking about the probability of failure. That's why they have derating for components, capacitors, resistors, and other components for temperature. Like ICs, you'll have derating specs for temperature and for vibration. So that's where, if you've got a system modeling tool and it can evolve itself to be able to produce or help reduce the effort to get to these artifacts that are absolutely needed. You're not going to be able to provide your model to the FAA or to the FDA, and that someone at the FDA or FAA is going to go through this, load the software up and go through the model. That's a huge selling point, because you're talking about shaving upwards of a man year or more of effort, of real effort. That's big money, and that's how you combat that. And if not, if you're not fully up to that, that's a big step. If you don't have it and you got to get there, that's a big step. But if you can produce ways to get there, or show them ways that you can actually use this system to help you get there, I mean, that's a huge win. I mean, that's kind of how you combat the cost. Is everybody's already selling them, I know how to make your design more efficient, your design process more efficient. But the other thing is just like, well, I know how to make your product development more efficient.
We have covered a lot here, and I can go on and ask you thousands of questions that we can bounce off, as we typically do when you and I sit and have a cup of coffee at the local coffee shop. But, I think we'd outlined the best practices when it comes to multi-board design. So, I want to thank you again for joining us and providing us your valuable insight. And I'm sure we'll have other discussions and other podcasts regarding the content of board design or system level design, or whether anything, has to do with producing and creating CCAs or PCBs or PWAs. So I want to thank you again, Chris, for your valuable insights.
Yeah, thank you very much. It's a pleasure to be discussing this with you on this platform. I enjoy it quite a bit. This is quite enjoyable for me to be chatting about things that I live, breathe, and eat.
Yeah, definitely. I know that for sure. So I've been to your lab at your house, so believe me, I know. So I want to thank everyone again for tuning in. So I hope you continue to tune in to our next episode, where we talk about electrical or electronic co-design.